Next, report acceptance and contract change order approval, secondary containment system evaluation. That's with Austin Love and Dr. Craig Benson.
Right. Thanks, Robert. Thanks, Mr. President. I'm just going to bring the board up to speed on a few things before we get Dr. Benson giving a presentation here. But just to review for the board, we're asking for two actions from the board. One, to approve Dr. Benson's report, which is what he's going to present on. And then two, we're also asking the board to approve a change order with Dr. Benson to basically have him attend some meetings in the future after his report is approved, meetings with Alyeska, meetings with state and federal regulators to promote the conclusions of his report. So those are the two actions that we're looking at the end of this item here. And I did just want to give a little history on the background of this issue, the secondary containment liner issue for the council. It's been an ongoing issue for the council in terms of the integrity of the liners that surround the tanks. It's kind of a multi-decade issue that we've been commenting on. And kind of fast forward to this past May, the Alaska Department of Environmental Conservation in May issued a condition of approval that is mandating Alyeska to take a couple actions. And it was written up here in the description, but essentially by October 2023, this October, Alyeska has to come up with some quote unquote preliminary methods to evaluate the integrity of the liner. So that deadline's coming up pretty soon. And then by March of 2025, Alyeska has to come up with some final methods to inspect this liner that over the years, there's been holes and other types of damage identified in it. So that was the decision from DEC this past May. I also just want to acknowledge that we do have Tiffany Larson from DEC here and Graham Wood here, as well as Allison Natcher. So I just want to appreciate them attending this, being here for the presentation. I know that they've shown interest in it, and it's just good to see them here, to be here for the report. So, what are we going to do with this information from Dr. Benson? Eventually, like I said, we're going to be promoting it to folks like Tiffany Larson and Graham Wood from DEC and to Alyeska to try to influence the preliminary methods that Alyeska is going to be coming up with by October of this year. So with that, I'm just going to give a quick introduction to Dr. Benson and let him take it away. So who's this Dr. Craig Benson? Why did we choose him for this work? Well, he has a master's and a PhD in civil and environmental engineering. And both of his advanced degrees actually focused on hazardous waste containment systems like the liners at the VMT. Dr. Benson spent over 40 plus years of his career developing tools, methods, and procedures for the design and evaluation of containment systems and liners and covers specifically, some of which are similar to the catalytically blown asphalt liner at the terminal. And just to give you an idea, that catalytically blown asphalt kind of looks like, roofing tar kind of, but it's really thick. That's underneath some soil at the terminal. And then over the length of his 2 decades plus career, he's straddled the line between academia and industry, coming up with those tools, methods, and containment liner procedures that are basically in use for containment liners and containment covers worldwide. So engineers use the practices Dr. Benson developed every day around the world. And I'll end on, currently he's the chair of Section 4 of the National Academy of Engineering. And that Section 4 is the Civil and Environmental Engineering Group. And the National Academy of Engineering is actually, you can think of it as, and these were Dr. Benson's words, the nation's engineering brain trust for who helps guide our nation in engineering best practices. So that's a little bit about Dr. Benson, and I'll let him take it from here.
Thank you. Thank you for those kind words. Great. Well, thank you, Austin, and thank you for everybody to have me present to you and share what we've learned, and for discussion, hopefully we'll have afterwards. It's been a really interesting project and builds on a lot of things I've been working on in my career for decades. But our basic objective was to look at tools to evaluate the integrity of the existing catalytically blown asphalt liners at the Valdez Marine Terminal, and then to develop some statistical methods that one could use then to guide how much area do I need to evaluate, and then based on how much area I've evaluated, make some inferences about the integrity of the liner. And that's in essence our scope. So if you could go to the next slide too, and we'll just talk through that. I will say that there's a detailed report that I hope you have an opportunity to read. This is the Reader's Digest version today. I realize you don't want to go through all the nitty gritty of this, but if there are any questions at the end that are lingering, glad to talk about them today or some other time. But we had two tasks, which are written out formally here, but really the first one in very straightforward terms is what are the best methods to detect and quantify the presence of defects in the CBA liner, importantly, without excavating. What are the tools, the best tools to go out and examine that liner without having to excavate? So-called non-destructive tools, because we're not digging it up. That was our first task, and we'll talk about the outcomes of that in a minute. And then second, let's assume that we are going to do an evaluation. How much of the liner do we need to evaluate? And how does that depend on what our objectives are? Does that, our objectives perhaps shift some, perhaps we need to look at different areas. And that'll come out of some of the findings from our study in a minute. We could go to the next slide. Well, one question you probably have is, why are defects important? In essence, say, from a lining system meant to protect groundwater, maybe that's an obvious question. But we often think of, a few defects here and there probably aren't problematic, but they can be in certain circumstances very problematic. This is particularly true with thin membrane type liners like the catalytically blown asphalt that's used at VMT, or so-called modern geomembranes, which are the polymeric materials, the heavy-duty plastic sheets that we do today. They're vulnerable to punctures. And I show that over here on the diagram to your left. I can't use my cursor, so I want to, but I realize I can't since you're driving it. But that's okay, I'll just talk through it. Imagine I've got that CBA liner on the surface. The whole thing's practically impermeable, but I have one spot in it where I've got a hole, right? And if that hole is over a permeable subgrade, like the gravel at VMT, what happens? Well, there's nothing to back up that hole, and it will leak extensively. And we all see this in everyday life. Your bathtub is essentially impermeable, but it's got one little hole at the low spot. And as long as that's closed, the bathtub doesn't leak. But pop open the drain and whew, the water flows out very quickly. That's exactly what happens in systems like this, where we have a thin membrane type liner with a permeable subgrade underneath it, like we have at VMT. And this is a well-known principle in our industry, and one of the reasons today we don't build liners like that. If we build membrane liners, when we build them, we put a clay component underneath, something that's relatively impervious that will block the flow of that liquid through holes. Today, we call those composite liners. They came out in the late 80s and 90s. Next slide. What causes defects and why should we expect them at VMT? Well, they are inevitable. We always have defects. There is not a liner built that's perfect. We have just installation shortcomings, errors. They always happen, no matter we do our best. There are some shortcomings that exist. Loading from equipment causing stress concentrations. We get heavy equipment driving over the liner. It's got a surface layer of gravel on top of it that will have stress concentrations that can cause punctures either immediately or over time. Oxidation and embrittlement. This is a particularly significant issue for asphalt liners. In fact, I was at a meeting last week looking at some degradation tests on asphalt type liners analogous to what's used at the site. And I was struck by how significant the asphalt oxidation was and embrittlement was over relatively modest time periods. That's a really significant issue. If we're going out and evaluating things, we can actually puncture it when we're evaluating with our construction equipment and lots of other different things you can just imagine. But you can see over here on the left, here's a puncture from at VMT in the CBA liner. That puncture is like your drain in your bathtub. That puncture's open, there's liquid pulled on top, it will quickly flow out the bottom. That's just the way it works. Next slide, please. So if I was going to summarize, we did an extensive review of different technologies that can be used, but it really boiled down to two. One called a leak location survey. These are the two that we ranked the highest. The leak location survey showed on the right. The other one called electrical resistance tomography, or ERT. That's very academic sounding stuff. But in essence, these two are very similar. The leak location survey is an electrical technique where we have a power supply and we have one of the electrodes going out to a wand that a technician essentially walks over the site with, and then we have another electrode which is grounded underneath the bottom of the liner. And that liner is an electrical insulator, except where there are holes. And that wand just goes over the surface, and if there's a hole, we'll get a signal from this device, and it will tell us, okay, the technician's over a defect, mark that on our survey, we've got a defect here, we got to go examine. This is an industry standard technique. It is used on projects all over the world on a regular basis. This is not new, novel stuff. This is standard practice. Another more sophisticated technique is ERT that I mentioned, but it's really similar. It's just instead of having an electrode walking over with a wand, we have a series of electrodes on the surface, a series of electrodes on the bottom, and we measure conduction between each and every pair. And then from that, we can back calculate and develop a map of what the surface of the liner looks like. And wherever there are defects, we will see current flowing through. It's just a more sophisticated version of leak location survey. These are the two best methods. Leak location's industry standard. ERT is a industry standard technique in geophysics, not regularly used in lining systems, but readily applied. Next slide, please. So that's really the end of the first task, is what are the best methods? And we went through a series of evaluation you can read in the report, but we had those two. The next question is, well, if I go do this, how much of the area should I sample, right? Should I just do, a 10%, 20%, the whole thing? And what does that mean in terms of some statistical confidence in what we're doing? So we developed a method to evaluate this. Actually, I did work like this in my PhD years ago and throughout my career, looking at similar types of problems using what's so-called Monte Carlo method, which is essentially brute force statistical analysis, where we simulate the problem on a computer that actually exists in the field. And what we did, looking at this slide here, you can imagine a tank farm here with tanks 7 and 8, or an area with tanks 7 and 8. And we created a grid corresponding to that area, recognizing we're not going to test under the tank. So it's a little bit smaller, and that's what you see in the middle. And we used probabilistic methods on the computer to simulate realizations or a case of a set of defects. Those are the blue points. So imagine that's one set of defects. And then and they're distributed randomly, both in number and in location. And we also conducted a random set. We picked 10 random sampling points, for example, as shown in this particular example. And we looked at, well, where I do a test, those are orange. Does it overlap a defect? If it does, then I got a hit. If it doesn't, I got a miss. And you can see in this particular example, I've got lots of places I've tested and lots of defects that were missed. So that's the method we used, and we have two important questions. How much area must we test if our goal is to identify and characterize the defects? How many there are, where they are, what size they are? That's one question. How much area for that? And the second question is, how much area must we evaluate if we just want to know the number of defects? Not necessarily exactly where they are or exactly what size, but I just want to know roughly with some statistical confidence, I have 10 defects. The latter question is important because engineers will frequently make calculations of leakage rates based on some accepted assumptions if we know the number of defects. So if I have a good handle on the number of defects, at least I can get a sense for what the leakage rate will be. I won't know where it will leak, or I won't know where the defects are to go and repair them, but at least I could say how many defects are likely there and how much is it going to leak under those circumstances. Two different questions. Next slide, please. We developed a whole series of outcomes and charts to be able to describe the findings from this, but the answers are really can be boiled down into two simple messages. On the left, how much area do I need to test to really characterize the defects, and to do that with some reasonable confidence. So let's say I wanted to measure 90, I want to make sure I capture at least 90%, right? I want to make sure that I get 90% and my probability that I make a mistake is less than 5 or 10%. Well, the bottom line is if you're trying to characterize the defects, identify them, location, number, size, you got to test the whole area. It's like 99% is what you need to do with statistical confidence. There's not a lot of difference between doing an evaluation of 99% and 100%. If you really want to understand where the defects are, size, location, test the whole thing. If I just want to know the number of defects, that's a different story. And in that case, I could say, we did an analysis and I can do calculations for the number of defects from the data that I would collect from a sampling and testing methodology over a fraction of the area. And you can look at the curves on the right-hand graph, and you can see they tend to level off around 20%. And you can go through some analysis and show that at least I need to do an evaluation over an area of at least 20% to get that standard deviation in my estimate of the number of defects down to a reasonable amount. If it's less than 20%, I may be able to estimate or extrapolate the number of defects, but it'll have so much uncertainty or such a large standard deviation that it's not particularly useful. So bottom line, at least 20% if I just want to know the number of defects. If I want to characterize the defects, it's test all the area. And I should say that we did this, I'm just showing you two graphs, wide range of conditions, varying the average number of holes per acre, and the looking at different number of holes in the system. Next slide, please. So just to boil this all down into some recommendations. First of all, the methods. We ought to be using leak location and ERT methods to evaluate the CBA. These are two well-established methods. And realistically, if you really want to understand whether these liners are functioning as intended and they've maintained their integrity, you ought to test the whole area. This is not a novel idea. This is what we do in our industry. You've got 50-year-old liners of a material that we don't use today because we know about some of its challenges. A very logical thing to do is to test the entire area with those two methods, or at least one of those methods, maybe both. If you just want to get at the number of defects, make sure you test at least 20% of the area, at least 20%. But if you want to detect and locate the defects, which I really think is what you want to do, then you really need to test the entire area. And again, I would recommend doing it in all of the containment cells. The other thing I would recommend too is like anything, this will be a bit of a learning curve to deploy this for the first time, and I would really suggest doing a pilot test with both the leak location and the ERT methods in the West Tank Farm area, which I understand is decommissioned. At least from industrial use, and at least test 20% of that West Tank Farm, and preferably all of it. And wherever you get defects from these methods, dig them up in that area, examine them, characterize size, shape, and confirm that the methods are working. So that's what I've got. I promised a Reader's Digest tour, but I'm eager to hear if you have any questions or would like me to elaborate on any particular component.
Thank you, Dr. Benson. Any questions? Jim Herbert.
Thank you again, Dr. Benson. I presented to some of the committees I've been on, and it's like in kindergarten, you repeat and you repeat, and then you start to get it. So thank you. One question I have, based on your experience, around the country, are there certain parts of the containment area that you think it'd be much more likely to have holes in them, that more emphasis should be placed upon if you were going to limit it to a 20% examination?
Yeah, that's a good question. I would focus on areas where I would expect greater stress concentration. So if I've got changes in grade, so if, for example, near an edge or near an appurtenance like a pipe or a tank edge, wherever I've got a change in the orientation of the liner, that puts concentrated stress in and will exacerbate the changes to the liner over time. So if I was going to pick an area, I would want to focus in those. I would suggest, though, from a trial perspective, is to try to get a broad area if you can.
And then one other, you answered it in our work group, but I think the whole board here should listen. What are the constraints associated with these two survey methods? We know there's a very heavy overburden, 4 or 5 feet over these liners. What other things would make the chore difficult? Thank you.
Yeah, no, good question. I think that the one issue, and this is one of the reasons I think the pilot test is particularly important, is the overburden is thicker than we normally deal with in industry today when we're evaluating liners. We do evaluate liners with these techniques that have material placed on top of them already. That's not unusual. 5 feet is at the high end that is done today. So I would want to get a sense for, am I going to have some resolution problems from that? So that's one challenge. And that's really the predominant one I see. The other thing is just you've got somewhat unusual geometry out there, so I think that's another challenge as well. But I don't really see that as something that's too difficult to overcome.
And just to repeat what I believe you said at an earlier session, if you were going to run one of these tests, you think it wouldn't be a 6-month project. Things would go fairly quickly.
Yeah, I mean, you could do this in a couple of weeks. Certainly the trial test, probably in a week you'd be done, right? Yeah, these are not novel research experiments. These are things that we do every day.
Dave Jenkins.
Thank you. I was wondering, I wasn't on those working groups with this, so maybe this came up, but, and I'm sure this is going to be related to amount of time and what kind of current voltage you're putting in for these detectors. Is there any issues with creating any electrolysis issues to any metal that's in that overburden there? And maybe there's no metal there, everything's isolated. I was just kind of curious if you've run into anything like that.
Yeah, good question. From what I've examined, if you have a lining system and you've got an appurtenance to it, so you got a pipe running through the barrier, if that liner is actually sealed around the pipe like it should be, right, then you shouldn't have any problems. On the other hand, if the pipe it's not sealed, so for example, if you've got a booter on the pipe and there's a defect in the boot where the stress concentration is, you will get a high level of conduction through that appurtenance or a pipe, for example. But that's not, that's actually just makes the defect show up even brighter. So while it would be a bit unusual anomaly, it probably would help you identify that defect even more readily. But it might cause some challenges in how we interpret the signals, but I don't think it would give you a anomalous signal that would cause you to draw an incorrect conclusion.
Okay, well, I was mainly wondering if your equipment causes any stray electrolysis in long enough period to make any problems with what's there.
Oh, no.
And one other comment I had that I was at the process of trying to figure it out reminds me very much of how the National Marine Fisheries Service tried to figure out and how to, how to sample a large shoreline with oil, lingering oil underneath, how to do this without digging up the entire beach.
Mm,
And their process was very similar. I'm not quite sure if I could put my hand on a report that went through how they went about it, but it was a lot of pit digging to make it happen, but very similar. Thank you.
yeah. I could see the similarity because the oil has a different dielectric constant than the water, right? It has different conduction properties. So would really, yeah, you get some bright contrast in that. That makes sense.
Any other
There's a
que-
couple people with hands up too. I don't know if
Yeah,
people are keeping an
no.
eye on that. Okay, sorry.
Yeah, got it. Robert Beadle.
Thank you, Robert. Thank you, Dr. Benson. Good report. I have two questions. You keep saying defects, and does it tell the size of the defect, or could it just be thin material? And the other thing is the test done better if it's like wet or dry? Would the electricity conduct better if on a wet day?
Yeah, two really pointed issues. Just to be specific, when I use the word defect in our parlance and our industry, that means a hole. All right. Kind of a nice way of saying you got a hole in the liner. So it's got a full penetration through the liner. Wouldn't be like a thin area or a scuff. It would be a physical penetration. So that was, and the methods, if there's a penetration, it will indicate whether that's the case. And the strength of the signal is generally in proportion to the size of that defect. So a smaller defect would have a smaller signal, and a larger defect, a larger signal, just because the conduction occurs more readily. There's some calibration to do as well. So if you were going out and doing a trial area, for example, on the West Tank Farm, you would get those hits from your leak location survey, and then you would go out and dig those up and examine them, and you'd be able to then develop a calibration for that particular overburden thickness of how big the defects are and relative to the signal. So that's kind of the first issue. I probably gave you a little more than you asked for, but I'm an academic, I can't resist.
No, that's fine.
The other parts about the wetness, the wetter, the better. This system is got 5 feet of gravel. So at the bottom of it, it's usually going to be moist. It almost always is, right? It doesn't have a way to really dry it out completely. But, if you really wanted it to be ideal, it would be right after it rained, right? Particularly heavy rain.
Okay, thanks for that.
Yep, you betcha.
Steve Lewis.
Yes, thank you. Dr. Benson there. Speaking of the area under the tanks, it seems to me that area has been subjected probably to more compaction and some variability in its loading over time as tank levels have gone up and down and tank maintenance has occurred. I would think intuitively that there would be a higher potential for damage underneath the tank than not underneath the tank. Have I got that at all correct? And moving from that, is there any way to check under the tank or not?
Yeah, first question is easier than the second question. Certainly you're right about the loading. You've got both high overburden stress from a full tank, and then you've got this oscillation in overburden stress as it's emptied and filled, right? And that will over time tend to cause the system to compress and then expand, and that can cause defects. I'd have to look at with regard to the conditions underneath the tank. I don't know the specific design detail on how the edge of the tank is bonded to the liner. Usually we'll have an angle type detail there with a wrap around the tank. And so assuming that the tank itself the bottom is impermeable, and that the liner is meant to capture spill. Under that scenario, the liner wouldn't be underneath the tank and probably wouldn't be inspected. If it's underneath the tank and that detail is not like the angle and wrap or clamp, as I mentioned, it gets a lot more complicated. And I don't know how to do that off the top of my head. So your second question's a stumper.
I could speak to that a little bit, Steve. This is Austin. We didn't task Dr. Benson with the under the tanks, but in some of our work with Taku Engineering, we have actually discussed that area under the tanks. And the way that I understand the construction of the CBA liner under the tanks is it is mated up to the concrete ring walls. So essentially there's another bathtub underneath the tanks. That's supposed to be where the CBA liner would catch a spill through a tank floor. But above the liner in the tanks, there's these basically PVC tubes that they use for cathodic protection system monitoring. And those tubes penetrate around the side of the tank like a bicycle spoke. So what Taku Engineering has proposed is, just kind of a off the cuff thought is if you plugged some of those CP monitoring tubes and then flooded it with water and then plugged it and then held it, you could do a hydrostatic test of underneath the tanks to give you an idea of whether or not you have a competent bathtub or not. It wouldn't tell you, of course, where the damage was, but it might give you an idea of if you actually have a competent secondary containment liner under the tank. So it'd be different than an electrical leak. You just basically fill your bathtub, let it sit and see what happens. But that's just been kind of a very preliminary discussion of potential.
You good, Steve? We'll move on. Bob Shabelson.
Thanks, Mr. President. And Dr. Benson, thanks. I learned a lot from your paper, but I couldn't understand a lot of it too. You made some superlative comment that all membranes leak or have defects or something to that effect. I don't want to misquote you. What was your statement there?
Well, that's in general is what we found over, decades of experience. It's very difficult over large areas to install a very thin barrier and have it defect free. It's nearly impossible. And that's why today in practice, it's pretty unusual for us to build a membrane liner without a fine textured earthen material below it, the so-called composite liner. Typically it's a clay liner, or these days we have something called a geosynthetic clay liner, which is a factory manufactured clay liner, but those two together form a composite. And so wherever there's the thin membrane does a lot of the work, but I know I got some defects in it. They're inevitable. And in those spots, I've got something backing me up. And that methodology has been really effective in practice. And the reason we use it is because our experience showed is that we could not install defect-free thin membrane liners over large areas. And even if we could install them, it's hard to keep them that way for years, right? It's not practical. And that there's really good literature on that. That was actually probably late 80s, early 90s, some classic work by J.P. Giroux and some of his colleagues at Geosyntec.
So defects are inevitable is what I'm hearing. And could you describe the state of the technology when this was installed in the early 70s? How does that liner technology compared to what you see today?
Yeah, a whole nother world, you might say. Now this is early 70s vintage, I think. It might be mid 70s. I can't quite remember the date. These CBA type liners were not unusual at that time. We don't use them today because we know the shortcomings with them. Our practice is to use factory manufactured what we call geomembranes, which are heavy duty plastic sheets. They're typically made out of high density polyethylene, which is the same plastic for your little Tykes toys. Heavy, just really bulletproof plastic. And there's a whole practice around how to install, weld, and test those materials. for containment systems. And that's largely what's used today. In even those systems, we build them as composites with an underlying clay type liner to create that system that has which we know has a very low leakage rate. But today we don't, the type of liner that's installed here is pretty unusual. You wouldn't see one today. You might find somebody building one, but it would be unusual. There is a new product out in our industry that started about 5 years ago, which is an analog to these materials, which are they're pre-manufactured bitumen liners, as they're called. They're like this material, but they come on a roll. And they've been marketed as an alternative to the polyethylene sheets. But some of the experience with that has indicated that those degrade much more rapidly and are much more prone to defects than the polyethylene liners.
Right.
In fact,
So
yeah.
is it fair to say that we collectively moved away from CBA liners because we understood that they weren't as good as the technology that came after them? Is that a fair statement?
I think that's a fair statement. Yeah.
Okay. Well, thank you very much. And I don't want to demean the science here. Again, the report was fascinating for what I could digest, but for me as a non-scientist, I don't think this is rocket science. I think it's pretty clear that the liner is degraded. And I don't know, I get a little frustrated that we have to do more studies and talk about it. From my perspective, it's just a matter of economics. If we know this thing was put down in the 70s, we know it's inevitable that it's going to have defects, then it doesn't meet the planning standard credit requirement. And I think that should be the first thing that we press for, is just say, this credit for the prevention standard should just go away, and then we can have the conversation, and Alaska can make the economic decision if they want to have the conversation on those terms. But otherwise, the way I read the rules, then you don't get authorization for a contingency plan if you don't have adequate containment. So I'm not going that far, but I'm saying we should at least have the discussion that we take away that economic disincentive in the way I look at it.
Yeah.
So thank you.
Thank you, Bob.
I would just add, any critical infrastructure, you inspect regularly to make sure it's functioning properly, right? Any critical infrastructure. That's just standard practice.
Anybody else? So Dr. Benson, I guess I just have a question about the base underneath that CBA liner, just knowing what it is and knowing the thickness of that overburden. In your experience, would you say that presents a problem as far as ultimately the age and the permeability of that liner? To be susceptible to damage.
One of the challenges with the materials that were used is that, we don't use gravels that are that coarse anymore right against the liner. We just don't do that because we know it creates stress concentrations, and those end up being defects or holes. So it does present a problem, right? Today, we wouldn't use that type of system. We'd have a fine textured material up below, and above it, we'd have a protective geotextile that would provide a cushion.
Got it. And going forward with the electronic methods, with the catalytic protection systems present any problem, you can probably figure that into the equation.
Yeah, any of the details, you just have to work around them. So,
Got it.
Yep.
Thank you.